Yeah, thank you. Thank you for the invitation to speak here. It's a shame I couldn't be at Los Angeles in person. I guess it's going to be quite a while, actually, I think, before we can travel internationally again. But well, this is the next best thing. Yeah, so today I'm going to be talking about some work that we've been doing over the last few years. Possibly some people here would have seen the talk along these lines before, but I will review and update with some quite recent results as well of a program that we've been looking at over the last few years of investigating critical phenomena in infinite translationally invariant matrix product states. I'm going to be talking about how do we detect quantum criticality in a matrix product system, the approach that we've been looking at, which is based around looking at higher order cumulants. And I'll show just some simple examples for some finite-sizing and POTS type models. And then at the end, we'll have a bit of a discussion about how we can generalize these beyond strictly local order parameters, that we can do the same thing and calculate higher cumulants also with string order parameters. And we can also do this for time reversal and also parity inversion operators as well. So it's a quite flexible kind of approach. Sorry, I was organizing that. Yeah, so there are quite a few approaches in the literature to detecting quantum criticality. Some interesting ones are based around bipartite fluctuations. So the entropy, for example, is really a key one. That this is the basic result from the area law violations in 1D quantum systems, that the entropy is going to diverge logarithmically at a quantum critical point. And if you look further at this, then you can get quite some detailed information, for example, by looking at the entanglement spectrum, by looking at bipartite fluctuations of the quantum numbers. And there's a couple of good papers on that, which I recommend to have a look at. Another somewhat related approach is to look at the transfer matrix spectrum, especially that determines the spectrum of correlation lengths of your system. So the correlation length obviously is a quite key property when you're looking at critical phenomena. So I guess there's some people in the audience who are maybe like new to this, who have been participating in the workshop and the tutorials. So just to review some of the properties, if our MPS is normalized, then by construction, we have an eigenvalue equal to 1, the largest eigenvalue, and the remainder of the spectrum, we can express this in terms of a spectrum of possible correlation lengths of our system as the negative 1 over the log of the transfer matrix eigenvalues. Alternatively, we can consider the inverse correlation length. So these behave much like energies. So there's actually some interesting papers. I meant to add it here as well. Actually, there's been a couple of good papers in the last few years about how to do scaling with respect to differences in these energies, and there's some advantages to doing that. Some other approaches would be scaling with respect to the bond dimension. So as we increase the bond dimension of the MPS, we expect that the correlation length will get longer and longer as we better approximate our critical state. As it turns out, scaling with respect to the bond dimension is a real pain. It's quite difficult to do. It's quite lumpy. The bond dimension is like an integer, so as you increase it by 1, it tends to do like quite a bit of a shock to your system. So it's very hard to get good results scaling with respect to the bond dimension. So what I'm going to talk about here mostly is scaling with respect to the correlation length itself, and especially focusing on order parameter fluctuations, so higher moments of the order parameters. Of course, for finite systems, there's lots of history behind this of calculating Binder cumulants and so on for finite-sized systems. So what we're really looking at here is how we can modify these kind of finite-sized scaling approaches to look at finite entanglement scaling as we scale the bond dimension of an infinite translationally invariant matrix product state. So to get an idea of what we're talking about here, this is a plot showing some of the transfer matrix eigenvalues of a transverse field Ising model. This is a very simple model. Probably most people here are very familiar with this. So the idea is that it's a model that has a quantum critical point as we adjust our control parameter through lambda equals 1 is the location of the critical point. And what we're plotting here is the spectrum obtained from the matrix product state transfer matrix spectrum, and this is represented as an inverse correlation length. So it's also something like a length scale. So there's the interesting key features here, I guess, is our lowest energy scale here actually isn't yet at lambda equals 1, which is a common feature that we see in finite size scaling as well, that our maximum entropy and point where our order parameters tend to diverge is not yet actually at the critical point, but it tends to scale towards the critical point as you increase your system size, or in this case, as we increase our bond dimension. So in this talk, I'm going to use M here is always my bond dimension, following the kind of Stephen White's, I guess, notation. Other people, I think, will use D or chi, but it's exactly the same kind of parameter. So as we increase the bond dimension here, the key features we see is that we get a collapse of energy scales. They're all moving down. At our critical point, the energy scale is going to 0, meaning the correlation length is diverging. But away from our critical point, this correlation length is actually going to converge to some finite value. So like the envelope here, that the lowest point here will converge to some value, but we're going to get a collapse of all of the excitations above that in our transfer matrix spectrum. And yeah. 30 and 40, and as it goes on, you can see that this will eventually all collapse down. So you can use this to determine, just from the correlation length itself, you can use this to determine where you have a critical point. Actually isn't an Ising model, it is an Ising-like transition, but it's actually, this is the first example I could find on my hard drive. And this is actually a two-species Bose gas that has an Ising-like transition as we adjust the tunneling between the two different species. And we can see here, this is now plotted as the correlation length on the y-axis and the bond dimension on the x-axis as a log-log scale. So we can see as we tune it right to the critical point here, which is the black dots, that's where we get exact power law scaling between the bond dimension and the correlation length. If we detune slightly away from the critical point, then what happens is that we're in a gapped phase, so our correlation length saturates, which we see here as a turning over of the curve here on the log-log scale. So that's the kind of the basic idea, and that's a good way of calculating critical points. It's fairly tedious though. There's quite a few calculations that go into this. So one of the themes that we're looking at is, are there ways to do this which are much computationally cheaper, that maybe we can be a bit cleverer in the kinds of quantities that we look at. So what we're going to do is calculate higher moments of our order parameter. So if we think here in terms of a local order parameter, I'm going to define my global order parameter M as a sum of on every site of some local parameter. So typically this would be, say, the magnetization. The sum of the magnetization on every site would be my order parameter. And we can express this in terms of moments. So I can write then my expectation value of the magnetization as this moment function M1 as a function of L. So clearly this is going to be a linearly extensive function. So it will be a first order polynomial in this case. But we can go on and we can calculate higher moments. For example, I can square my operator and I can calculate the magnetization squared, which will now be a second order polynomial in a system size. And more generally, I can calculate my kth power, which will be my kth moment, which will be a polynomial function in the system size. So rather than writing this in terms of the moment functions, it's much more convenient to write this in terms of cumulants, specifically the cumulants per site, kappa. And the moments in terms of the cumulants have a well-known form here. So the first cumulant is essentially just the same as the first moment. The second moment expands into a part which is a quadratic part, which is just the first moment squared, so like the order parameter squared times L squared, plus the remainder part here, which is the second cumulant. So this is the variance. So when we calculate the second moment, we've got a part that diverges as L squared, which is the order parameter squared. The remaining part that diverges linearly, linearly extensive with L is the variance kappa 2. And we can go on, and there are expressions for this for all orders. So the kappa 2 is the variance. So at least for classical systems, this is closely related to the susceptibility. Kappa 3 is the skewness. So in distribution theory, that tells us about whether my distribution is skewed, say, to the left or right. Kappa 4 is this kurtosis, which kind of tells me, in some sense, how flat it is, or looking at the shoulders, whether the shoulders are kind of spread out or kind of very narrow. Now, a key point as to why this construction is useful is that these cumulants per site are well defined for translationally invariant infinite MPS. So it's possible to calculate these moments. You can obtain them directly as a polynomial valued expectation value. So there's an algorithm which is described in this old fairly old paper by now. Here, so the output of this algorithm is directly the prefactors of the polynomial expansion of the moment function. So from that, we can essentially read off all of the cumulants as a value per site. Now, that's quite interesting because I think that's about the only way that I know of, actually, where you can calculate these cumulants in a quite rigorous way. So I don't know, for example, how to calculate these cumulants per site for a finite system. Perhaps if someone knows of anyone that actually does this for a finite system, I'd be quite interested in learning about that. Okay. So at a critical point, if we're sitting at a critical point, then all of our cumulants have a power law scaling with respect to the bond dimension. So my kappa I is going to scale with my bond dimension M as some critical exponent, which I refer to here as alpha I, as the exponent attached to the ith cumulant. And this is just an example from the Ising model. So this is the log of the bond dimension here on the x-axis, and the log of the corresponding cumulant on the y-axis here. So this first cumulant is just the order parameter. This one's the variance, and the power 3 and the power 4 of the order parameter. Okay. So now to look at scaling functions. For a finite system, we scale with respect to the system size L, and for a quantum system, we're going to have a control parameter, which is how far away I am from the critical point. So for a classical system, we'd replace this with the temperature, but we're looking at quantum critical points here. And in general, we'd also have scaling with respect to some external field as well, which I'm not going to look at today. So the key exponents that we're going to be looking at is the correlation length exponent. So that tells me how quickly the correlation length diverges as I tune my system towards the critical point. The magnetization or the order parameter exponent beta, which really tells me how quickly my order parameter goes to 0 as I approach my critical point. And I've also got gamma star, which is my variance exponent, which tells me how quickly the fluctuations of my order parameter diverge as I approach the critical point. And we have a scaling relation that these are all connected, that 2 beta plus gamma star is equal to nu. And just to emphasize at this point that we're looking at 1D quantum systems, we don't have a fluctuation dissipation theorem, which in 2D classical systems would tell us that the variance here is just simply related to the derivative of the magnetization as I impose an external field. That we don't have a fluctuation dissipation theorem in 1D, or at least not in the same form. So the version of this scaling relation for 2D classical systems would be 2 beta plus gamma is equal to nu times the dimension here, which would be 2. Okay, so from this we can write down some finite size scaling functions, which is the typical approach if you're going to do some kind of finite size scaling analysis. And from these we can do scaling function collapse and so on. But what we want to see is what are the corresponding scaling relations if we're looking at an infinite system. So if we've got an infinite system, really the key point here, the key replacement is that we have some kind of effective system size, which is given by our correlation length of our system, which at the critical point will scale as our bond dimension to this new exponent kappa. So this is a new exponent that you don't see in finite size systems, but this is really the relationship between the bond dimension of the MPS and the correlation length. So the general prescription is that we take our finite size scaling relations, wherever we see an L, we replace it by an m to the power kappa, and we attempt to find a new scaling relation now with respect to the bond dimension. So instead of our scaling relations that relate t times L to the 1 over nu, we'll have our scaling functions that are functions of t times m to the kappa over nu. So we can write down again scaling functions for finite entanglement case. Now, to derive the relationship between the variance cumulants, I'm not going to do that in detail, but just this is how it's done for classical systems. We just take the singular part of the free energy and we write that in terms of a scaling function of T here, which would be the reduced temperature and the external field. Again, we can write that as a finite entanglement version in terms of the bond dimension, and we can obtain the different cumulants as derivatives of our scaling function with respect to h. So as we go through this, we see as we take each higher derivative, that pulls down another factor of beta plus gamma times kappa over nu. So what we see from that is that we get a relationship between all of the exponents, that the exponent of my nth cumulant is going to, well, I can write that in terms of my beta and gamma exponents as the nth exponent is n minus 2 times beta plus n minus 1 times gamma star, all multiplied by kappa divided by nu. So in particular, really the low order exponents are the most useful ones. So my alpha 1 is essentially the beta exponent, and my alpha 2 is basically the gamma exponent. Now, interestingly, this actually also works if we extend this backwards to alpha 0. So if we like look at the 0th order cumulant, and this turns out to be actually just the correlation function, the correlation length itself. So it actually makes sense then to define my 0th order cumulant as the correlation length, and then I can express all of my relevant, or all of the important exponents in terms of these kappa parameters. So then my cumulant relation, I can write it then as a sort of self-contained expression. Given any two exponents, I can write down any other of the exponents. Probably the most useful form is if we write it in terms of the alpha 1 and alpha 2, or it's also possible to write this in terms of the alpha naught, the correlation length, and alpha 1, the order parameter. So that gives me all of the exponents for any higher order cumulant. And to see how this works, again, for an Ising model example, this is from a paper with my former PhD student, Jason, who did a lot of this for his PhD thesis. So, for example, what we have here is for the Ising model, the first cumulant, which is just the order parameter. So we can see how that scales as we increase the bond dimension, then we get closer and closer to the thermodynamic exact result. Similarly, for kappa 2, for the variance, we see that that's diverging as we increase the bond dimension, and so on for kappa 3, the skewness, and kappa 4 actually changes sign as we pass through the critical point. And we can write down the finite entanglement scaling functions of these. So if we plot it now as, I guess as written as b here, it really should be lambda. As if we plot it as m to the power kappa over nu, then we can get a scaling function collapse as a function now of the bond dimension. So this is actually not a bad way of determining from first principles what the values of the exponents here, alpha and kappa over nu, actually are. So you can just adjust these until you get a nice scaling function collapse, and then that determines the values of your critical exponents. It's a little awkward though, because again, we've got bond dimension scaling, we've got the m, the bond dimension explicitly appearing in here, which is not a very easy way. Yeah, so there's a question, I think, from Thomas. Yeah.
Yeah, I'm on you now. Yeah, so okay. I have to say I was a bit ignorant about the cumulants, but it's very interesting. So in this example, in this plot here, so did you plug in known exponents to get this nice collapse, or how did you determine these kappa and nu in this case?
Yeah, so these are actually the known exponents, because the lines don't perfectly overlap.
Can you maybe also comment on like how you so the definition of the cumulant you gave for finite L, right? So you define it in terms of the magnetization or the magnetization operator. So you get for the cumulant sort of for expressions you got sort of m squared and so on in terms of cumulants and powers of L.
Right.
How exactly do you define it for the infinite system then?
Right, so yeah, so these are the expressions. Okay, so for a finite system, I think it's really hard to calculate just those cumulants individually. You can calculate the moment function, you just calculate the expectation value over your system size L, and you just get some number. So for an infinite system, you can imagine that we just calculate our order parameter over some finite but large section of my system.
You just have it L.
And then that will be that will be some polynomial in L, and we can imagine kind of what happens asymptotically as I make that region bigger and bigger and bigger. Then I would expect that asymptotically that the prefactors of my polynomial will converge to some to some fixed value, which I could calculate. Now, the algorithm we actually have is of course much more sophisticated than that. It just calculates this directly from looking at the spectrum of the transfer matrix. But that's conceptually what we're doing. We're looking at the asymptotically kind of like large region where I can sort of like express now all of my cumulants in terms of polynomials of this sort of L parameter.
Cool.
Does that sort of make sense?
Yep, thanks.
Yeah, okay. Right. Yeah, so we can also do this for the correlation length itself, so our kappa naught, if you like. So again, for the Ising model, as we increase the bond dimension, we can see that the correlation length starts to diverge as we get closer and closer approximations to the critical point. Again, we can write down the scaling function of the correlation length itself, and again we get a nice scaling function collapse. But what we want to do, again, we've got the bond dimension here. We really want to avoid that because if you're scaling with the bond dimension, it means that you need to really work hard to get your MPS converge as well as you can for that particular bond dimension. And that's quite difficult to do. It means that you need to, well, there are some special tricks you need to do in your algorithm even to achieve that. And what we'd like is a procedure that doesn't really depend on having extremely good convergence. So we want to have some scaling functions that don't use this bond dimension here explicitly. Okay, so in order to get there, we're going to kind of do it a little bit backwards. And the next thing we're going to look at is how to actually find the critical point in the first place. What's the best way of doing that? So for finite systems, it's pretty common that the people will use the Binder cumulant. So there's an example here. We can kind of ignore the figure on the left for the time being. The figure on the right, again, it's an Ising-like transition. It's not actually the Ising model. But the Binder cumulant, essentially this ratio of the fourth moment to the square of the second moment. This is quite special because if you calculate the scaling function of this, then the system size disappears at the critical point. So if you calculate this ratio of the moments at the critical point, it has some universal value that's independent of the system size, at least up to corrections to scaling. So you can see that quite easily when you plot this Binder cumulant. Well, on the left-hand side here, we've got various plots here for different system sizes. We can see that it approaches the exact transition point actually only relatively slowly. But if we look at the Binder cumulant, then already from the smaller system sizes we have available here, we can see that we get that they have the universal value at the critical point already. So the question is, how do we write down something like a Binder cumulant for an infinite system? So if you just naively do this, if you just take the large L limit, it just doesn't produce anything particularly useful. So for example, if we're in a regime where our order parameter is non-zero and we just take that limit, then what happens here is that the term that dominates when you calculate the fourth moment is just a term which is the L to the power 4 part, which is just the order parameter itself to the power 4. And again here, this one just becomes the order parameter squared, the order parameter squared, and square it again. So that just becomes 1. So we just get a constant. On the other hand, if we're in a regime where our order parameter is 0, then our moment expansion simplifies a little bit, but then we just get 0 here. So you just get a step function, which is actually not too surprising that that's actually what you expect to see if you take the infinite size limit of your Binder cumulant. You just get a step function. So the original approach that we used in the 2009 paper is that we actually just evaluate the moment polynomial. That is, we just go back to our moment functions back here, and we evaluate these using L, where we just fix the value. L is equal to something proportional to the correlation length of our system. And that actually works reasonably well. But there's actually a better approach that we came up with since then, which is far more in the spirit of the original Binder cumulant, which is just to simply find a combination of cumulants such that the bond dimension cancels from our expression. So the way we do that is we just find, if we just calculate some arbitrary product of the cumulants, kappa naught to some power a naught, kappa 1 to the power a1, and so on, then that scales with my bond dimension as the power times the corresponding alpha exponent. So we just find a particular combination such that that exponent in the end is 0, and then that kills off the dependence on the bond dimension. So the simplest possible case then is this so-called second order cumulant, which is just the kappa 2, so the variance divided by the square of the order parameter and multiplied by the correlation length. So this is a pretty similar kind of operator to what people do for finite size scaling, like the second order cumulant of the moment ratios, the second moment divided by the square of the first moment. The difference here, I guess, it might look a little strange as to why the correlation length appears here on the bottom. Actually, it's kind of obvious as to why that appears there if you think that what we're calculating here is the cumulants per lattice site. So just from dimensional analysis, in order to get a scaling quantity, we need to multiply our cumulants by a length scale. So if we do that, then we'll have a length scale here, and length scale is here, so we end up with like a 1 length scale on the bottom. It's also possible to calculate.
Sorry, yeah, I just wanted to know that you're running out of time, so it would be great if you could.
Oh, right, okay, right. Yeah, okay. Yeah, so we can also calculate higher order cumulants, so closely related to the Binder cumulant. I also looked at this one, which I think is the lowest order cumulant that doesn't include the correlation length itself. So since we're running out of time, yeah, I have actually more or less shown the main the main results here. So if we show this now for the Ising model, this is now as a function of very low bond dimensions here. So this is our second order cumulant here. So we can see that if we have bond dimension 3 and 4, it's not so good. 4 and 5 is not so good, but already bond dimensions 5 and 6 give us a very good approximation for our critical point. We can go on, in fact, as a better approach. What I'd recommend actually, because even this is calculating quite a lot of data, if we just look at this ratio here, so kappa 2, kappa 1 over kappa naught, so this is something that we expect will be independent of the bond dimension if we tune to the critical point. So here, if we tune at lambda equals 1, right at the critical point, if we look at this as a function of bond dimension, is essentially flat. Whereas if we tune it even just slightly away from the critical point, then we see that it goes haywire quite quickly. So this, I think, is probably the best way we have at the moment to actually find critical points. Since I'm basically out of time here, I think I'll probably just flash up a couple more slides. So we also did some examples for the quantum Potts model, the 3-state quantum Potts model, which is slightly less trivial than the Ising model. We also see very nice results in this case as well. And we can also go on, so we can use now the scaling of these to find some critical exponents just by fitting kappa 1 versus kappa naught and so on. And that's really the key point I was going to show. The remainder, I was just going to, that we can generalize this beyond local order parameters. So I guess if anyone wants to know about this, then come and talk to me sometime. But we can generalize this to string order parameters. We can also generalize this that we can treat time reversal also as a kind of a local order parameter as well, that we can treat this as an MPO where we do a complex conjugation, and I'll finish up here with our conclusions. Yeah, thank you.